in terms of the chemical terms, we're talking about which one has a higher bond strength, what is the nature of the reaction in that bond breaks easier on one versus the bond on another one. The compound T-butyl bromide and T-butyl chloride have structural formulas that we frequently write this way. Now, one of the rate factors is changing the nature of the compound, changing the structure. So if you can see that in one compound, the only difference is one has a chloride attached to the central carbon, and the other has a bromide attached to the carbon. Well, the carbon chloride bond and the carbon bromide bond are different in energy, or the bond strengths are different. And so as a result, that's going to affect the rate at which the reaction proceeds to products. Now, what we find, and I wanted to make a note here, typically these are abbreviated T-butyl chloride and T-butyl bromide, so I'll be using that for the most part in the work we're about to do. As we go through this, we'll get some of the specialty information and formula weights and the like for each one. They're in 100% solution right now. Okay, the reaction we're going to run is called a Solvolysis reaction. A Solvolysis SN1 substitution reaction. It's a very simple type reaction, and there is another type of reaction called an SN2 reaction, and you'll learn about that in organic chemistry. But in this one is a reaction that proceeds in two parts. And the rate depends upon ease of ionization of the carbon halide bond. So what we see is, what we'll do is we will add a portion of the T-butyl halide into a 50-50 alcohol water solution and monitor the rate changes in the T-butyl chloride and T-butyl bromide using the techniques that I show you in a few minutes. So taking generally T-butyl X being the chloride and the bromide, that's a general symbol for the halides, plus H2O in IPA. Now IPA has to be present in the solvent system but to enhance the solubility of the T-butyl halide. T-butyl halide by itself is not soluble in water, but if you make a binary solvent by including some isopropyl alcohol, ethyl alcohol, which mixes in all proportions with water, then this will go right into solution and you will get the reaction that you are trying to study. Well, what happens is in the H2O, maybe you know, maybe you don't, this is always ionized into a hydronium ion, or H plus, and the hydroxide ion, minus, not OH minus, in that the outcome of this is the OH will replace the halide in the T-butyl halide and give you T-butyl alcohol, and have an HX as also a product. Now HX is a strong acid. This is monitored, the yield of the H halide, the HBr and HCl is monitored using pH electrodes. And if you look at the handout that you're given, you'll see the raw data is pH versus time. So there'll be a real-time measurement. We'll start here above 7. That's just the nature of the alcohol of water. It runs about 8. And each reaction, we start at the same point. Well, at this point, there's no hydrogen generated. As a matter of fact, the at 7 is 10 to the minus 7. And that's so small we assume that there's no hydrogen. But when the halide, T-butyl halide is added, that halogen comes off and hooks up with H, forming the strong acid, and there's a very rapid drop in pH. And so the only reason this drops like that is because of that formation of the mineral acid, HCl and HBr in the two cases. If you look at and from this we can determine the rate loss based on the data and position, and I'll show you that in just a second. Okay. Now, this SN1 reaction, just in passing, SN1 mechanism occurs in two steps, as I mentioned up here in the note above. And what that means is, first step, you have the T-butyl halide, and when you put it into the water, it goes to T-butyl positive ion plus the halogen, like that. And the rate, K1 if you want to, rate depends on the strength of bond. And you can have an indication of this from delta E bond energy. I'll just put in parentheses. From the two halides. One is a carbon chloride bond, gives a delta H bond energy, and I'll look it up in a second. And this bromide, delta H B is equal to, so these are the bond energies, the amount of energy given up when the bond is formed. The higher that bond energy, the stronger the bond. So the stronger bond, one with a bigger number between the two, is harder to ionize and has a slower reaction. So your expectation in this experiment is the T-butyl chloride rate will be less than T-butyl bromide rate because of differences in bond energies. Okay, now since the objective of the experiment is the rate law for Solvolysis of T-butyl halides of the T-butyl halides, period. So, knowing that the T-butyl halides plus an IPA H2O mix gives T-butyl alcohol plus HX, we want to write the empirical rate law for this reaction. Now, to save us all a lot of time in the past, have done this, you assume reaction is zero order in the H2O. That means that H2O, if you write the rate law expression, will fall out as 1. IPA doesn't enter the reaction at all. It's only there as a solubility factor for the IPA in water. So, therefore, reaction reduces to T-butyl halide IPA H2O. So we'll need to put it up there, let people know what we're working with. Goes to T-butyl alcohol plus the HX, okay? So up to now, you should follow me pretty well, right? Now, write the empirical rate law for this reaction. Well, the rate law is always in terms of what? The first of the reactant side. And so in this case, rate is equal to K, molar concentration T-butyl halide, chloride or bromide, raised to the X power. So that is your empirical, and your job is to determine, so to speak, K and X. Well, the problem is, in this form, you can't measure what changes in what rate is as a function of concentration and get a K and X because it's an exponential function. However, if there's a way to convert this to a linear function, then you can determine what K and X are very easily. So if I took natural logarithm of both sides of this expression, what I would wind up with is this. Right there, which translates to, and I'll move this around for a second, X ln of T-butyl halide plus ln of K, and all that equals ln of rate. This is of the form y equals mx plus b. Which is a linear function. So from the data that's in front of you, if you can get y, a series of y's for three concentrations, and a set of x for those three concentrations, you plot the two-dimensional graph. The slope of that line that you get is your order of reaction, and the intercept is your ln of k, which is K is the ln of K is equal to e to the minus ln of whatever it is over there, because you'll be in the negative quadrant. So what you're going to find when you plot this is that you're going to be in this quadrant right here in X and Y. And of course this is negative X's over here, negative Y's. But this axis here, this is your X, will be Ln of T-butyl halides. You got to get it in moles per liter and stuff based on, and I'll show you in a second. And this one be Ln of rate, right here. Numbers you get out off of this side. And what you have when you do these is a graph that goes here, and this point right there is at Ln, hear me, listen to me, focus, Ln of concentration, not concentration, Ln of concentration at 0, right here. So this is Ln of rate at Ln of concentration equal 0. So this is where it's very important that you see what I'm doing. The Ln of T-butyl halide at 0 equals 0. This term that I've got bracketed right here becomes 0. What happens to the rest of the equation? Ln of rate at concentration 0 equals Ln of K. Right there, and K is equal to E to the L minus, actually this will be a minus number when you get it. It's actually E to the plus, but it's the value is a minus value. So it's minus Ln of rate that you have here, and that'll give you your rate constant. And that's how you get your rate constant out of this. So what we want to do, now this is your raw data here. And so we want to translate a couple of things. One, the X values in our expression, I'll rewrite it, Ln of rate is one of the values we want to get, is equal to K Ln of the molar concentration of the halides, in this case chloride, plus Ln of K. Now that'll come after we plot X and Y. So what we need is Ln of rate, Ln of concentrations, which are your X values, and an Ln of corresponding Ln of rate for whatever X value you use. And that's your Y values. You're going to plot those. Okay, so how do you get the Ln of T-butyl chloride? Well, we need to concentration effects and test, let's see, how we do this, volume of T-butyl chloride in milliliters. It'll be 1 mil, 2 mils, and 3 mils that you see on your graph. So you can see where it says 1, 2, and 3. So by increasing the concentration, we notice directly there are changes in rates because we're generating the lower pHs faster. Okay, the thing we need to do is convert this to moles per liter. Now we're going to use, let's see, did it tell me? So you're given 50 milliliters of IPA and H2O, then what is your concentration of the T-butyl chloride right here? Of course, that's moles over volume in liters, like that. So if you inject 1 mil into 50 mils up here, you have 51 milliliters of T-butyl chloride. Now, 1 milliliter of T-butyl chloride per 51 milliliters, because 50 and 1 milliliters of solvent. Okay, I'm going to move this so we can work this out. All right, 1 milliliter of T-butyl chloride, I'll have to go online. So what I did is I took the density times the volume, so that many grams in there. Now the formula weight is 0.851 over whatever that formula weight is for the T-butyl halide. So I put it in converting to moles per 0.051 liters, and so we'll have the molarity that we need for the T-butyl chloride right here. Molar solution. Now, our plot requires Ln of T-butyl chloride for the 1 mil. So that would be Ln of the T-butyl chloride is equal to Ln of 0.18 molar. Well, it's already in molar. And that's a negative 1.71. Okay, so that's your X1. Now you repeat this for 2 mils. 2 mils T-butyl chloride gives it's a little different than this, but for arguments we'll just double it, okay? So a minus times 2 is a minus 3.43, because you're going to be putting 2 mils and 50 mils, that's 52 mils, so you're dividing by a little different number, but it's pretty close to that for what we're doing. And then 3 mils would be 3 times that minus 171. And so 5.13. So you have 1 mil, 2 mil, 3 mils add-ins for your concentration, and this is going to be good for all 3 calculations, which is 1 mil, 2 mils, 3 mil. You're going to have 3 rates that you have to deal with in here. I had everybody plotting 3 graphs, but I'm just going to do one for you, and you do the other 2. So what we've got here is your X values in that expression. So now we need Ln of the rate, so we can plot it versus those Ln of concentrations. So what's the issue here? It's changing concentration, 1, 2, and 3 mils. What's going to happen? We're going to have 3 rates. This is your reference right here, and then you have rate 2 and rate 3. Well, what's going to happen to the rate? What do you expect it to do? Okay, it's going to increase the first order, second order, something like that. So it's either going to double or go 4 times and that kind of thing, so you can apply the exponent. That's what we're getting at. So how do you get the rate? Well, when you go into your graph for your rate 1, you just pick like here. Like 1 mil, we have at 50 seconds, we had a 2.906 pH. Now, this is a measure of the hydronium ion generated, or the HX generated. And then this is a bromide. I wanted the chloride. We're working on chloride. Now, there's a chloride. So at 50.04 seconds, you had this pH, and then 70 seconds, you had 2.703, and 90 seconds, you had 2.573. Well, across here, at 50, 70, and 90 seconds, you can calculate a rate for each one of those and plot, and this will give you your Y numbers against the 3X numbers, because you'll translate this, you'll get this as a rate change in concentration over time. That'd be 1 mil over time, over 50 seconds or something. I'll show you, we'll work it out. And then and that will be your first plot right here, 1 mil. Then 70 seconds, it'll be here for 1 mil, and then here for 1 mil after 90 seconds. Okay? If you go 2 mils, it'll be the same thing. It'll be this over this time, and then 3 mils, this over time. Okay, I'm just going to pick 1 and plot it. So we want 1, 2, and 3 as pH numbers, and then I'll and convert that to rate. Okay? Okay, so what the data is given is a pH 1, 2, given data, not date, A, there we go. pH values is 2.906. The next one is 2.388 pH at 50.04 seconds. That's what I should have done. Okay, and then third one was 2.287. Okay, I need to condense that. 50.04 seconds. Okay, now, like this. Okay, well, what does pH mean? It is a measure of hydrogen generated. So the amount of hydrogen generated in moles per liter can be calculated 10 to the minus pH right here. So I can take each one of these, go 10 to the minus 2.906, and then 10 to the minus 2.388. All this is in moles per liter, and 10 to the minus 2.287. And so you have 3 concentrations. This is the concentration of HCl generated as well in our reaction. Okay, so that is I get 0.0012 molar. Let's see, 0.0041 molar in hydronium. That's 0.0052 molar. Now, from this you can get rate because we're at 50.04 seconds. So it is the rate is now equal to the concentration of hydronium ion generated over 50.04 seconds. Yes, sir.
So are we doing the T-butyl core?
All right. These are the numbers that correspond to the values. So all I did was take the exponential pH at the power of 10 based on base 10, and then I got the concentration of hydrochloric acid generated in 56.67 seconds. And then I took those concentrations over time, which is the definition of rate, and it generated those 3 rates. Now, the Y values in our plot that go with the X values are ln of rate. So what we need to do is convert these into ln of rate, which is ln of 1.55 times 10 to the minus 5. They're all still in molar per second. And then ln of 2.44 times 10 to the minus 5. And this one's ln of 3.15 times 10 to the minus 5 molar per per second. And so we get three numbers out of this one. And this one is a minus 10.4. Minus 10.6. Minus 11.1. So if we have x against y's, minus 11.1, minus 10.6, minus 10.4, and our x values. Okay, so out of our plot, where x is equal to Ln of the concentration of T-butyl chloride, and y is equal to the corresponding Ln of rate in that plot, and we plot it, and the slope comes out to be the slope comes out to be the order of reaction. Now, the accuracy of this experiment that we're using demands we round it to the slope to the nearest whole number, and I'm just giving you that. Intercept K Ln of K equals Ln of rate at Ln of concentration equals 0. That means whatever you get as far as that K is e to the whatever Ln rate is in the plot. We have Ln of T-butyl chloride here, and over here we have Ln of rate, like this. Of course, that's the 0 point. Minus 1.7, the max is 5. So we'll make that max here. That's a 5.13, and then it's something weird here. Uh-oh. It's 3.43, 5.13, and I'd say 3 would be, say, right here, and 1, about 2 right in here. And then we go down to 11, 11.1, make that one a 10.6, and pretty tight in here, 10.4. So 1 and 11.1, that'll be here. And then there's, I'm going backwards, 10.6 and 3.4, 4.3 be right in here, and then 10.4 and 5.1 be back over in here. So now we plot a line through that. See, I don't remember them going up that way. So right here, that looks like well, it's bigger than 11, so I'll say 12.5 or something like that, negative 12.5. These are negative values. Did I plot that right? Let me check. Okay, this number is your ln of rate at 0. Well, at concentration, ln of concentration is 0. but it also equals ln of the k value. So ln of k now is equal to a minus 12.5, and k equals e to the minus 12.5, whatever that comes out to be. And I get a 2.68 times 10 to the 5th as mole per liter per second. Here's the error right here. When I got 1.71, I just doubled it. Wrong. You double concentration, you don't double the ln numbers. So what I did is I doubled it and put it in here and redid the computation for the ln of concentration in 2 and 3. And so you need to change your x values to those values, and then we'll have the correct sequence. So this is incorrect here. Such is the nature of science. You plot it and you go back and you look and make your correction. So we have a 1.71 here, and we still got the 11, the minus 11.1 right there. So that starts, somewhere around here. But these should have, wait a minute here, that's the high number. So this is minus 1.71, say minus 1.02, and a minus 0.62. We'll move that over a little bit, like that. Now, we come over here, now it looks right. Come to here, and then probably, well, we'll put 10.4 up here. Let's see. Move 6.2 over here. Like this. Put a line through there. And that was a minus 10.4. This is ln of rate, ln of concentration. We'll run this through the dots best we can. This is ln of rate equals ln of k. And that value right there goes to, I'll say, 9.5, minus 9.5. And so now we got the right data in place. So ln of k equals a minus 9.5 gives us a k value, e to the minus 9.5, and whatever that comes out to be. (9.5) negative second e to the x, second scientific. Yeah, that's 7.5 times 10 to the minus 5. So there's your K value based on 1 mil, 2 mil, 3 mil injections. Now there are 3 plots in there. You do number 2 and 3 and put them on the same graph. You can use the techniques they use in Excel if you want to. But everything that you need to make the calculations, then you take the average. This is just K1 based on that first block of data. You need your X values, your Y values. These are your X and Y. And remember, ln rate is equal to X ln of concentration, in this case chloride, plus ln of K. So that's what you're trying to plot. The slope of that line right here will tell you that it is first, second, or 0, or whatever order. Actually, a straight line like this is first order, just from the graphic that we're using there. I would suggest taking the numbers and plotting them on Excel using a scattergram. If you don't know how to do that, I can show you after the exam how to do it, but I want you to work on these, and you can apply the same sequence of calculation to the T-butyl bromides, and when you get the K value for that, compare it to the K value for the average you get for the T-butyl chloride, and draw your conclusion. Since one is faster than the other, what does that tell you about the bond strength? And so forth, like that. So this is due after the exam. Well, probably we want to do acid-base chemistry, and then when we give you the second exam in a couple of weeks, then it's due then with the acid-base. The last experiment we'll do will be a solubility test of calcium hydroxide, and that'll finish your lab work. But anyway, this is a big boy experiment. Go through the data and information I gave you, and work up the other times and pH values. You have graphs, two graphs, one for TBC, one for TBB, and in each graph you'll have 3 straight lines. Now theoretically, those 3 will all go through the same point, and it doesn't usually happen, but you take the average of it and use that as your average K value that you're going to compare to the other halide.